Remember back in the beginning when I talked about exponents for a hot sec and then we didn't really talk about them for a while? Well, it's because we really didn't need the exponents for linear functions, which is just the variable raised to the first power. We've kind of exhausted everything that we can do with linear functions. So now we need to kind of bump up our algebra skills and learn about exponents. Well, we already learned about them, but you get to learn how to work with more complicated exponents. Here, let's remind ourselves what the definition of an exponent is. If we have x times x times x multiplied by itself a certain amount of times, and we will say it's a times, any amount of times that it's multiplied together, it means that we have x raised to the exponent of a. It's just repeated multiplication. And this rule isn't restricted to variables. We can repeatedly multiply constants. I'm going to teach you a bunch of different shortcuts when it comes to simplifying expressions with a lot of exponents kind of jumbled in. And, well, how can exponents get more complicated than just the definition? That's the point. They're no different than the definition. We'll be proving every single one of them, why they exist, why they work, and I will constantly be referring them back to the definition, which is this. Let's see if I can screenshot that and put it up in the corner or something, just so you can be looking at it all the time. If we have a string of x's multiplied together a certain amount of times, and then we have it being multiplied by that same variable raised to a different amount, or the same. A and B could be the same, but it can be different. A certain other amount of times we can multiply that thing by itself. That's the same thing as x to the a plus b. I know what you're thinking. I thought we were doing exponents, which is higher on the order of operations than multiplication. So exponents are clearly very far away from addition. But it's not addition on the baseline where all of these bases are. This multiplication is on the baseline, indicating I want to multiply this term by this term. Here, the addition is up in the exponent. So it actually, if we're doing order of operations properly, we would actually resolve this plus first. It's kind of in parentheses in the exponent line. Not sure if baseline or exponent line or superscript line is the formal definition, but I might refer to it as superscript line or baseline or even subscript line. Yeah. Let's prove this real quick. I do think the definition isn't going to be too helpful, other than I'm going to kind of copy and paste it. So if we have a bunch of x's multiplied together, you know what? I'm just going to completely color code this. I have the colors. I'm going to use it. All right. Really formal stuff going on here. So let's multiply this x by itself this amount of times. Then this multiplication kind of gets carried down to connect these two terms. I'm not changing anything about what's going up there in our shortcut. I'm just rewriting it in definition from the definition of an exponent. Well, here, this looks like, this multiplication, even though I've color-coded it blue, isn't any different than any of the other multiplications. That was just a way for us to follow my work. I'm over-explaining my shortcut, which is actually I'm losing time, so actually you owe me time right now. What does this mean? Yeah, if this is all one string, I'm just looking at it as, well, I have A of them, and then I also have B of them. Well, we already did that, so that wouldn't be showing anything. It would be x to the A plus B. I can do an example to kind of prove what's going on here. So for an example, we have x to the 2 times x to the 3. Really easy because I'm running out of room. X times x is this x squared, and then big times, I don't want to have to keep color coding everything, x times x times x. Well, that's 5 x's multiplied together, so that's x to the 5th, and you can kind of see 2 times 3. You can kind of see that 2 plus 3 equals 5. Boom! We can do the same thing with division of a bunch of the same variable. Okay, so here I'm saying that we have x to the a divided by x to the b this time. A of them up here, b of them down here. The shortcut is x to the a divided by x to the b. Unsurprisingly, is x to the a minus b. Instead of multiplying and then adding them like we did up here, multiply and then add, we're dividing them, so we subtract. Here in this setup of the proof for this thing, it's kind of easier to show if I have an unarbitrary amount of x's, so we're actually going to just go straight to the example. X to the 5 over x squared. Using the definition of exponents, I'm going to expand these exponents out as their repeated multiplication form. I could rewrite this as x times x over x times x times 3 more x's. This algebraically works out to be the same as this, top times top, bottom times bottom. We know that. But then we also know that anything divided by itself is 1. So this cancels out. Cancel meaning it's equal to 1. 1 times 3 x's multiplied together is x to the 3rd. So basically what we're doing is canceling out the same amount of x's on the top and the bottom, as long as, until we have no common variables on the top and the bottom. Cool. I'm repeating myself. The astute among the viewers here could quickly call me out and say, in this example here, A was bigger than B. We were left with x to the 3rd, which is positive. But when we subtract, we could potentially get into the negatives even if both A and B were positive to start. If we went and did the problem as a reciprocal, we would only have 2 x's on top, but then 5 x's on bottom. By that same logic, we would cancel out 2 pairs of x's. We're left with 1 on the top over x cubed. By the shortcut, we would also rewrite it as x to the 2 minus 5 is negative 3. But we haven't talked about negative exponents yet. Do negative exponents even exist? Does that just mean that the whole thing is negative? The whole term is negative?